Didn't even give us a chance.
Yeah. Figured you guys figured it out already. So. You see how I did it? You just start breaking it down slowly. So Jessica, what I was doing there, first of all, this minus, plus, minus, plus, minus, plus, or in this case, plus, minus, plus, minus, plus, minus, can always be handled by negative 1 raised to a power. Either negative 1 raised to the n or negative 1 raised to the n plus 1. Because if you think about it the way it works, the natural numbers, if you go in a sequence where it's like odd, even, odd, even, odd, even, odd, even. Right? So if every other term is positive, then you just need to make sure you're in that part of the parity where you're always getting n squared or n to the 4th to generate the positive number. Right? So in this case, you see I'm starting from a negative number, so when n is 1, so I looked at this as n is 1, 2, 3, 4. When n is 1, you know you want it to be negative. When n is 2, you want it to be positive. 3 negative, 4 positive. So I just inserted the negative 1 to the n in there to generate that. You also see as these terms increase, just looking at the numerator. So what I'm saying is look at it, break it down into pieces. Don't look at it as a whole. You know, so this takes care of this minus 1 and it takes care of the plus, minus, or minus, plus, minus, plus. Then look at the numerator. You see when n is 1, the numerator is 1. When n is 2, the numerator is 2. When n is 3, that's an easy one. That's just an n, right? And then you look at the denominator, you look at the numbers 4, 9, 16, 25. Those are all perfect squares. So you just have to make sure you're starting at the right place. When n is 1, we really get 2 squared. When n is 2, we get 3 squared. When n is 3, we get 4 squared. When n is 4, we get 5 squared. That's why I made it an n plus 1 squared to make sure it's matching up. So you guys understand that?
But how am I supposed to know that?
You're supposed to figure it out because you're smart enough to get into Stetson.
That doesn't mean anything. I've met some really dumb people here.
Me too. We actually had a talk about that. Me and some admin types, because you know, in the math department, we see everything from the brightest Stetson student to those who should not have been admitted to Stetson. And when I was talking to her, she mentioned that she was doing interviews with students over the course of the last year, and she realized from the interviews with the students that there's a general attitude amongst the better students at Stetson that they're disappointed and they're kind of upset that there are these students who really shouldn't have been admitted in there because they're just slowing the class down, they're just kind of getting in the way, you know what I mean? So the administration's aware of that, actually, and they're kind of taking stuff. You know, if they raise the admission standards, I'm all for it. So but you know, they're doing it at the same time trying to increase enrollment. That's always a delicate balance, you know what I mean? How do you raise the standards and increase the enrollment by 20% all at the same time?
Well, I mean, even if you raise the standards, you know, someone could have gotten a miracle ACT score.
Right. It certainly does happen. All right, so let me get started on the idea of a limit. Yes, but at least you know what this is, Jessica. As much as you might despise it, you know what it is. Which is why I'm such a proponent of teaching this kind of stuff in calculus.
Okay, so what's an upside down A and a backwards E?
Right, which is why you should have taken my class, Luciana.
It's evil is what it is.
It's evil. It's a spell. It's the evil ancient hieroglyphics. No. So this upside down A means for all. Let me decipher this. I gotta go through and annotate it for you.
No. Something. I didn't like this part.
I kept getting
Well,
names mixed up.
Here's the good part.
Is why you're saying no.
I'm not actually requiring you guys to prove stuff using this definition, unlike in Calc 1.
Yeah.
But I want you to see what the formal definition means. So you're not going to encounter any problems where I say solve delta as a function of epsilon, which is what I had you guys do back then. But by doing so, you kind of have some familiarity with all this cryptic jargon, right? So it kind of moves us forward a little bit. So that's a description here, the symbols and what it means. Let me draw you a picture.
So M is replacing delta now?
Yes, M is replacing delta now. The reason it's different in this case, Jessica, is because when we talked about limits in Calc 1, we talked about finite limits, so the limit as x approaches a. Here, notice the limit's going out to infinity. So it's a little bit different. And I think a picture will really explain this better. So let me go ahead and plot a sequence. And as you guys already, pointed out to me, that when you plot a sequence, what you actually see is a series of dots. Right? You don't actually see a continuous curve. And moreover, on this axis, remember, this is going to now be the natural number axis. So you have, year 1, year 2, year 3, so on and so forth, like that. So when we say that the limit of a sequence exists, in this case, what would the limit equal?
0.
Good. Yeah, so in this case, we're talking about the limit of the sequence equaling 0. Well, according to the definition, what that means is, for any possible positive epsilon you choose, so somebody choose a positive epsilon for me.
25.
Okay, make it a small number, because epsilon is 2. How about 0.2? You like 0.2?
Okay.
All right, let's try 0.2.
Well, I thought we were using natural numbers.
Oh, okay, let me be specific. The n is the natural number. Because you see, the output for a sequence can be fractional.
Okay.
Right, so it's only the input, the domain, that's defined on the natural numbers. Everything else can still be fractional and logs and trig functions and all that kind of stuff. So you choose some very small epsilon. I'll put the epsilon right here. This says for any epsilon you choose. Actually says for every epsilon you choose, but there's no distinction in the math language between for any and either way. Take my logic class block that, not here. So you choose any positive epsilon, there must exist a positive m, such that the distance between these 2 points is less than epsilon whenever your domain element is greater than m. And here's what I mean by that. If this is your epsilon, let me go ahead and draw a strip out here in association with the epsilon.
What is M?
I'm going to show you. Just give me a second.
So you didn't say that.
Not yet. So you choose an epsilon. Do you see that there is a point, specifically here, Luciano, here's your m, such that if you go beyond that value of m, all of the points in the sequence are contained in the strip. Right? But this definition must be true for every epsilon, which means if you choose a smaller epsilon than the first epsilon you chose, let's choose instead of 0.2, let's make it like 0.02 or something.